265 people died over Belle Harbor on November 12, 2001, 2 months after September 11th. The vertical stabilizer came off in flight. The National Transportation Safety Board investigation into the disaster was structured into 6 critical areas of analysis, tracing the sequence chronologically from the flight path and wake encounter down to the structural failure, the systemic human factors, and the final safety mandates.
Section 1. The Climb and Wake Encounter. Page 1 of the official NTSB Aircraft Accident Report establishes the factual baseline of the flight. Flight 587 was a regularly scheduled trip from John F. Kennedy International Airport to Santo Domingo. The Airbus A300 605R was carrying 2 flight crew members, 7 flight attendants, and 251 passengers. Before takeoff, flight data recorder data confirmed the first officer initiated a standard rudder pedal check. He swept the pedals left and right to their maximum deflections. The aircraft was functioning precisely as designed as it taxied out behind a Japan Airlines Boeing 747.
The operational timeline covers a span of just 3 minutes. At 09:11:36, the local controller issued a standard wake turbulence caution. Less than 2 minutes later, at 09:13:21, the captain transferred control, stating, "You have the airplane." Climbing through 1,700 feet, at 09:15:36, the aircraft hit its first wake turbulence encounter. The flight data recorded a 0.04 G drop in longitudinal load factor. This is an entirely routine aerodynamic event, essentially just a mild bump. Yet, exactly 22.5 seconds later, at 09:15:58.5, the vertical stabilizer completely separated from the fuselage.
The wake generated by the preceding JAL 747 was calculated by investigators. On page 56 of the report, the NTSB documents its exact strength, quoting directly, "The predicted circulation of the wake vortex at the times of the apparent encounters would have been between 63 and 80% of the vortice's initial strength. The atmospheric conditions that morning were highly favorable for a slow rate of vortex decay. The vortex was roughly 100 seconds old at the time of the encounter, right before it would have naturally dissipated."
Section 2. First Officer Rudder Inputs.
Flight data recorder data captures the specific mechanism of the disaster over a 6.5-second interval. The first officer responded to the wake turbulence with a series of rapid alternating rudder pedal inputs. The sequence started with 0.1 inches of left pedal movement, immediately reversing to 0.1 inches right, then 0.2 inches left, accelerating to 0.7 inches right, and finally ending at a massive 3.9 inches of right rudder travel. Over those 6.5 seconds, the control wheel was also moved 7 distinct times with extreme peaks left and right. This was a severe cyclic control input.
During the investigation, the NTSB reviewed a prior event involving this exact first officer. In 1997, an American Airlines captain reported that the first officer rapidly stroked the rudder pedals 1, 2, 3 at an altitude between 1,000 and 1,500 feet following a wake encounter. According to page 12 of the report, the captain pointed out to the first officer that his use of the rudder pedals was quite aggressive, but the first officer insisted that the American Airlines Advanced Aircraft Maneuvering Program, AAMP, directed him to use the rudder pedals in that manner. The investigation definitively isolated the aerodynamic effects of the wake from the aerodynamic effects of the pilot's manual inputs. The rapid pedal movements induced a severe buildup in side-slip angle, meaning the aircraft was yawing violently broadside into the relative wind. Page 149 of the report makes the following conclusion. The Safety Board's airplane performance study revealed that the resulting motion of the aircraft, including the hazardous buildup in side-slip angle that eventually led to the high loads that resulted in separation of the vertical stabilizer, was solely the result of these rudder pedal inputs and was not associated with the effects of wake turbulence.
Section 3. Vertical stabilizer structural failure.
The rapid yawing subjected the composite vertical stabilizer to massive structural stress. The stabilizer was connected to the fuselage by main attachment lugs. Because of the excessive side-slip angle, the aerodynamic loads generated on the tail reached approximately 2 times the limit load design envelope before separation even began. The wind force produced a resultant lug force of roughly 905 kilonewtons, triggering a catastrophic tension failure directly at the main attachment points.
The component met all U.S. certification standards, and there was absolutely zero evidence of fatigue or pre-existing degradation. On page 136, the NTSB report states, "The vertical stabilizer fractured from the fuselage in overstress, starting with the right rear lug, while the vertical stabilizer was exposed to aerodynamic loads that were about twice the certified limit load design envelope and were more than the certified ultimate load design envelope.
Section 4. Human Factors and AAMP Training.
The NTSB analyzed the human factors that conditioned the first officer's fatal control responses, focusing heavily on the American Airlines Advanced Aircraft Maneuvering Program, or AAMP. The AAMP simulator exercises contained highly artificial constraints. To train pilots on extreme upset recovery, the simulator was programmed to roll the virtual airplane past 90 degrees. Crucially, the programming completely inhibited the ailerons and spoilers for 10 seconds or until a 50-degree bank angle was reached. Pilots were unaware of this suppressed control effectiveness, which forced them to rely heavily on the rudder to recover from the artificial roll.
This dangerous reliance on the rudder was reinforced during classroom instruction. The NTSB reviewed a 1997 videotape of an AMP ground school session. Page 86 of the report records the exact instruction provided by the lecturer to the crews. Now, some of you, pilots attending the AMP training class out there might say, well, I'm going to use a little coordinated rudder to help the nose come down. Fine. That's good technique. Coordinated rudder in this context meant moving the control wheel and the rudder pedal in the exact same direction.
The AAM flight training booklet explicitly cited wake turbulence as a factor in loss of control incidents and presented the rudder as the most effective roll control device. The NTSB documented this systemic training flaw directly. On page 141, the board concluded, the American Airlines Advanced Aircraft Maneuvering Program ground school training encouraged pilots to use rudder to assist with roll control during recovery from upsets, including wake turbulence. The investigation uncovered an industry-wide lack of awareness regarding variable stop rudder limitations. Pilots simply didn't know how sensitive the pedals became at cruise speeds. On page 143, the report details this knowledge gap. The safety board concludes that, before the Flight 587 accident, pilots were not being adequately trained on what effect rudder pedal inputs have on the Airbus A300-600 at high airspeeds and how the airplane's rudder travel limiter system operates.
Section 5. Rudder System Design Characteristics.
The design of the Airbus A300-600 rudder travel limiter system was another critical factor. It utilizes a variable stop design intended to mechanically restrict physical rudder travel as airspeed increases. At 165 knots and below, the rudder has a maximum travel limit of 30 degrees. However, at 250 knots, the flight speed during the accident, the maximum travel is limited to just 9.3 degrees. At this speed, full allowable rudder deflection is achieved with only 1.25 inches of physical pedal movement. On the ground, it takes substantial force to push the pedals to their maximum travel. In the air, at 240 knots, a breakout force of just 22 pounds allows for full allowable deflection. The NTSB analyzed this sensitivity across multiple aircraft platforms, as noted on page 146. The safety board concludes that the Airbus A300-600 rudder control system couples a rudder travel limiter system that increases in sensitivity with airspeed, which is characteristic of variable stop designs, with the lightest pedal forces of all the transport category aircraft evaluated by the safety board during this investigation. Prior to the accident, Airbus had issued documentation addressing the structural risks of aggressive rudder usage following previous structural overload events on other flights. An Airbus Flight Crew Operating Manual Bulletin, cited on page 115 of the report, carried an explicit warning. Whatever the airborne flight condition may be, aggressive, full, or nearly full opposite rudder inputs must not be applied. Such inputs can lead to loads higher than the limit or possibly the ultimate loads and can result in structural damage or failure.
Section 6. NTSB Findings and Changes.
The investigation culminated in a definitive ruling that synthesized the aircraft's sensitive rudder design, the flawed AMT training, and the actual control inputs recorded on the flight data recorder. On page 160, the board determined the official probable cause. The National Transportation Safety Board determines that the probable cause of this accident was the in-flight separation of the vertical stabilizer as a result of the loads beyond ultimate design that were created by the first officer's unnecessary and excessive rudder pedal inputs.
Immediately following the probable cause, the board outlined the systemic conditions that precipitated those inputs. Also on page 160, the report states, contributing to these rudder pedal inputs were characteristics of the Airbus A300-600 rudder system design and elements of the American Airlines Advanced Aircraft Maneuvering Program. The investigation proved that even a structurally sound aircraft can be torn apart if flight crews are conditioned to operate outside its aerodynamic envelope. The question remains, does current simulator programming accurately reflect the structural realities of commercial flight, or merely artificial scenarios?